Okay. Right. So then we discussed during the introduction all these fun experimental investigations of this force here, but we've already discussed that. So let's move on to some other stuff. Now, the other thing that you'll want to remember from your previous course is how we talk about energy in a system of charges. Oops, no, it's not. So we want to talk about energy. Do you prefer the bolder, fatter lettering to this, or do you not care too much? You prefer the bolder, okay. So energy, and in order to talk about energy, we need to talk first about work. And the way we talk about work, of course, is by talking about the work necessary to move a charged object in the presence of other charges. And you remember from basic mechanics that the work applied to a certain object is just going to be the integral of the force that you apply to it. So let's say that we have 2 points, A and B. And what we're going to do is we're going to move a particle along a certain path from A to B. So what are we going to do? This particle is a charged particle, and it's got spectators around source charges that create for it a force. And the work that we will have to do in order to displace this particle from A to B is going to have to work against that force. So therefore, the kind of amount of increased energy given to this particle is minus, because we're going against the force, the integral from A to B along the certain line that you'll consider here, dl, dotted into F. And here I'm just using F as the force acting on the particle as I do this. Okay, so this is a line integral whose limits are given by vector positions for the end and beginning points. Okay, the differential line element, of course, is when you're integrating here on the thing, you'd have a little section here, and this would be, for example, a little dl. Right, so the little dl would have a magnitude corresponding to the length of the step you're taking here, and the direction corresponding to the direction in which you're moving. Okay, line integral. So that's the work that's applied to the particle as we go from this place to that place. Okay. Yeah. So that's all fine. Now, so let's just say. Sorry, I should. So say that we have a fixed source particle. So SRC is source particle. And we're going to put that one at R is equal to 0. Okay. And RS is equal to 0. And this one is going to have charge QS. Okay, so so essentially, when we compute this integral, let me just squeeze it in here. So we're going to do the integral, or maybe I'll just use it and just do it in a different thing because I might want to do a little drawing. So okay, what do we have? Let's draw again our 2 points. Maybe I'll just redraw the 2 points. Point A here, point B here. And now what we're going to want to do is go from A to B, but there is now a particle at 0, right? So this is vector 0, and there's a Q source here. So now the point is that when I move the particle from A to B, I have a choice of very many different paths. I can go like this. Okay. I could go in a different way. Yeah. All paths would give a certain answer. Now, what is the easiest path that I can consider? Well, of course, the point is that there's going to be a radial direction from the origin to A. And then I can imagine a path where I first keep the same radius and go to the direction marking particle B. And then from that point onwards, just increase my radius until I get there. Okay, so my path of integration from A to B is going to be this one here. First an angular bit and then a radial bit. Now the point is that when I want to calculate this minus integral from A to B dl of f, the force itself is purely radial. Therefore, in the angular part of the integral here, the force and the displacement are orthogonal, they're perpendicular to each other, and therefore this dot product vanishes. The only non-zero is along the radial bit that I have here. So, really, what that means is that if this has a q test here, the integral of the force is just going to be minus q test q source over 4 pi epsilon 0. But then it'll be an integral just in the radial coordinates. I'm just going to have to go from the radius RA to the radius RB, where this length here is RA. And then, well, you know, do I need to write it? So this particular radius here, that would be just RB. I'm going from radius A to radius B along the radial direction, dr, and it's just 1 over r squared. Okay? So therefore, the answer for the work that is done here is just the result of this integral here, just going to be q test q source 4 pi epsilon 0. And then I've got the difference, you know, so I just get minus 1 over r, there's another minus sign here, and I evaluate it at rb at minus ra, so it's just 1 over rb minus 1 over ra. Okay, so please tell me that you've done that repeatedly in the past. Yeah, I think you have seen energy in systems of point charges. You remember that the energy of this configuration is just proportional to the inverse algebraic distance between the particles. Question? There's an extra minus sign here. So when I integrate 1 over r squared, I guess minus 1 over r. And then I evaluate from RB to RA. So the minus coming from the integral gets absorbed by this minus, and then I evaluate at this boundary first, minus at that boundary. Right? Okay, so that's the answer that I have. So that's the so for two charges, labeled with whatever what you want. So here QS, QT at their respective positions, RS and RT. We just have that the energy of that assembly is just this this expression. Yeah, so 1 over 4 pi epsilon 0, and then the product of the charges, QT QS or QS QT, whatever you prefer, divided by the vector difference, the norm of the vector difference between the two, RT minus RS. Okay, 1 over R, 1 over R, 1 over R, 1 over R. Okay, so it's normal. The force is like the derivative of energy. Yeah, it's minus derivative of energy, and therefore the 1 over R energy that you have here gets translated into Coulomb's force. So in a sense, we could also have said that the law for point charges is that their energy is the inverse of the distance times the charges. That would be a completely equivalent statement, provided we accept the basic laws of classical mechanics, just motion. Okay, is this all cool? Like total revision material here from your first course, right? You are hopefully not learning anything here. Okay. Then for an assembly of charges, then of course, the way you would do this, well, maybe a first comment here. You always have in these reasonings here a kind of basic situation where you've got all of free space available to you. And therefore, if I ask you to consider a certain assembly of particles, you can kind of in your mind start with particles extremely far away at the other side of the universe. They don't talk to each other. They don't have any joint energy at all. Therefore, if I've got an assembly, the way I'm going to compute the energy is that I'm going to first bring one charge. I bring one charge in to where you want it, and then that is completely for free because there's no force acting on that one. There's nobody else. And we don't count anything about the particle acting on itself. You know, acceleration, deceleration, and whatnot. We don't do that. We imagine that we bring it from infinity, infinitely slow to a particular position, which takes just a long time, but you do it. And then once you've got one, you bring in the second. So the second one sees the force coming from the first. And then the third one sees the force coming from the first two. And then number three sees the force coming from the first three, etc., etc. Okay, so the way you can write the expression for the total energy assembled in this system is again this annoying constant. But now you say that you bring in all your particles from 1 to your n. Let's say you have big N of them. But now you are computing the work coming from the force which is due to the ones that were there previously. Okay, so when you bring the jth in, it has to be greater than I. Okay, but now again, this qi, qj divided by rij. And again, here I'm kind of accelerating the notation by writing it like that. Okay, and I could even just write rij, maybe as an exercise. You know, let me even do that to make sure that you. Yeah, so this is just like the distance. Okay, am I going too fast with the notation? Scalar rij is the norm of the algebraic difference between the two vectors ri and rj. Right? Don't confuse this. You can also just symmetrize this sum here, because you see here we've got a summation of j greater than I or not. Mathematically, this is going to be absolutely exactly the same as 1/2 of the full sum over everybody. So for 8 pi epsilon 0. But now I'm going to sum over the I from 1 to n, and I'm going to sum for all j different than I. So you see in this case here, I just like sum things twice over, but I've got an extra factor of 1/2 compared to this, so I get the same answer. Okay, so this is just the expression for the energy of an assembly of charges. Okay, all cool, right?